All right, well, good afternoon, everyone. Welcome to our session on air quality. And I'm Steve Young. I'm a retired longtime U.S. Environmental Protection Agency employee and currently co-chairing DSIP's Air Quality Cluster group with Beth Huffer, who was here a moment ago. I think she stepped out again, but Beth is my fellow co-chair. And we're here today to talk about advances in air quality sensing and the dissemination of data. So let me one more time encourage everyone to please sign into our shared group document, the top bit.ly and QR code that you can see here. And also feel free to browse the resources document, the lower document. There's Beth rejoining us. I just mentioned you, Beth, as my fellow co-chair. No, I didn't say anything bad. So I will, I had a bunch of things I was going to say, but in the interest of time, let me just say estimates of the global burden of poor air quality are that 7 million people a year die excess deaths. In other words, poor air quality has caused people to die prematurely, if you will. So 7 million people a year. Poor air quality is a hugely consequential issue. And we're seeing increasing interest in no small part because of wildfires. That's attracting a lot of attention, wildfire smoke. So we're seeing a lot more interest, a lot more concern, and some really important advances in capabilities. I want to open today's session, though, with Magali Sanchez Hall from Wilmington, California, which is part of the city of Los Angeles. I don't totally understand the structure of Los Angeles City and Los Angeles County and all that stuff. And I need to bring up my notes with intro stuff. I want to give what I can say is, I'll just say it quickly. Here we go. Magali is an environmental justice activist, and she's the founder of Emerge, which is a movement to promote environmental justice through reverse engineered community engagement, bottom up in a nonlinear and intentional approach. I won't go through her degrees, but they're online and you can peruse them. And Magali has really impressed me. Wilmington is an underserved community that has some pretty major issues, including poor air quality. But I will turn it over to Magali in just a moment once we get her presentation up on the screen. And let me see if I can successfully do that. I might need your help, Sherry, but let's see what happens. Okay, hopefully you can see Magali's presentation up on your screen. Those of you who are remote, and we're going to try to make it full screen. This is, yeah, we can move. Yeah. Okay, Magali.
Yes. Can you hear me?
Yeah, give us one more second. I think this is okay, isn't it? Yeah. So, okay, Magali, take it away and just give me a next slide, please, when you want me to advance.
Correct. Thank you so much. Thank you for the invitation and for having me here. And thank you for all the audience also for being here and choosing this session. My name is Magali Sanchez Hall, as Steve mentioned, and I just want to give a little brief background of Emerge. Emerge is in Spanish, by the way. And I just wanted to say it was founded in 2015 when I took an environmental law class at UCLA, and the presenter showed a slide with a picture of a house and a church, and she said, this is ground zero for pollution in the whole United States. And it turns out it was my house or my brother's house and the church. And from then, I found out all the environmental racism that was taking place in my community, as well as all the environmental injustice. And when I finished school, I went straight back to my community, started working and making sure that we could do some research and also some background on why all of this was taking place, including a community case study of Wilmington through UCLA. Next, please.
I'm working on it.
That's okay. And on the next slide, what I want to show you is that more or less, I want you to visualize what Wilmington looks like. And I want to tell you of the sources, all sources of pollution and the industries that we have around. We have the largest port in North America with a massive movement of goods. We have 5 refineries surrounding Wilmington, including one of the largest one in the Southwest called Marathon. And then we have an average of 1 million trucks moving in and out of the port through the streets of Wilmington. We have a massive amount of container yards all around us. And we also have energy plants for the Department of Water and Power that supplies all the energy in the city of Los Angeles. And also other sources of pollution. We have warehouses, trucks, garage, metal companies, and many others. Next, please.
There was.
Next, yes.
I got too tricky moving. Here we go.
The next slide, this slide shows you the city of Los Angeles map. And as you can see, the area with the green that connects the city of Los Angeles at the bottom, it's Wilmington. And on the right-hand side, you will see the Wilmington map, and all the area on purple or kind of pinkish, that's the area where massive industry of the Port of Los Angeles, the refineries, and all the stationary pollution it's sitting in, plus also the mobile sources of pollution that are not accounted here in this Wilmington map. Next, please. In this map, you can also see on the pink area, the industries of the refineries, the Port of Los Angeles surrounding. In the middle, you can see that's all residential area with a massive, dense populated areas. And you can see the 710 freeway, which is one of the arteries that takes out most of the goods and trucks routes, and also the Alameda corridor, and also the 110 freeway. Those are the only 3 ways of transferring or transporting all these containers that are coming through the port. And also we have the railroads that also are taking out all these containers and oil. Next, please. I want to give you a little bit of background and demographics of Wilmington, and considering this as it's considered, Wilmington is considered a disadvantaged community based on the Senate Bill 535 in the state of California, which is high levels of pollution, a lack of green spaces, proximity to hazardous waste and industrial facilities. It has a high cost of living, high levels of poverty, low education attainment, and about 90% of the population in Wilmington are Latinx or Hispanics, and also 40% are foreign-born, majority from Mexico. And about 50% of the residents 25 and older do not have a high school diploma. And the average income, individual income, is $24,000. So you can see how this is basically a really disadvantaged community. Next, please. I wanted to show you in the next demographics screen shots that I took of some of the demographics from Wilmington. And I wanted to just make sure that you understand that I used the pin drop on census tracts from the zip code 90744, which is majority Wilmington. And the reason why I had to use the pin drop is because I had to make sure that they qualify for the Justice 40 initiative by it was executive order by President Biden. and that they do qualify for all sources of resources that were supposed to come down the pipeline for disadvantaged communities. Next. So this is the community information and the breakdown of race by race. And as you can see, the number of households is 14,034. And the breakdown by race, Latinos basically are 90%. And the life expectancy is 79 years. Compared to Beverly Hills, it's 10 years under. So 89 for Beverly Hills, Wilmington, 79 years old. And also the breakdown of the income per capita is 20,428. Next, please. This is a slide that was taken, one of the screenshots that was taken from the LA 100 equity strategies in the Wilmington case study that I led, and also for the community engagement reverse engineer presentation, and was published with also the LA 100 equity strategies in the National Renewable Energy Laboratory out of the Department of Energy. Next. This, if you check the weather right now, the air quality in Wilmington, this is most likely what you will find. You will find that the air quality in Wilmington has a great air quality right now. It's green. Even though I just told you all the sources of pollution we are confronted by. So is this environmental injustice or environmental racism? I want you to think about this. So some of the toxic releases from the facilities surrounding Wilmington are in one of the highest percentiles. And we're talking about, if you look at the screen and the color of the screen right now on the map, and the toxic you can see that it's all gray, and it's in the highest between the 90 to 100% percentile. Next, please. So one of the issues that we have high levels is the diesel particulate matter, very high as well. And this is between the 80 to 90 percentile. And just imagine through the residential areas and residential zones, we have this 1 million containers a month moving in and out from Wilmington. And as you know, most of you know what this particular matter can really harm the community and the children, mostly in Wilmington, from asthma. And the elderly, as well as the children, are very sensitive to the effects of diesel particulate matter. Next. The asthma percentiles are also really high, as you can see in this map. And we're also going again from the 80 to 90 and close to the port of Los Angeles, which is Harry Bridges, where all the containers and trucks are coming out. You can see it's 90 to 100% percentile of, and majority of the children in Wilmington, if you go out on the streets and ask, they will tell you that they have asthma or somebody in their families. Next, please. One of the issues also that we're having and confronted with is a cardiovascular disease percentile. Compared to the county of Los Angeles, Wilmington has the highest cardiovascular disease. And we are talking about greater than 90% of in Wilmington. Next. This is an issue that we are confronted with, and it's a problem. It's a huge problem because we have very few air quality monitors. A lot of these air quality monitors are managed by the Air Quality Management District, and we have two main ones that are measuring particulate matter 2.5 and COs, ozone. And these are in the border of the city of Harbor and Wilmington, and the other one is in Long Beach in Signal Hill, which is pretty far from the area. So we're not really capturing the air quality as we should. And that's why most probably you can see on your phones when you check the air quality that is good. We talk to the community, and the community is ready to place this indoors or outdoors in their properties if we have access to air quality monitors. We want to collect data and analyze the air quality of Wilmington properly, because it is not, and that it's proven, it's a fact. So, and also we want to really measure and find a baseline of the amount of toxins and chemicals that are truly prevalent in this neighborhood and areas. Next, please. In the reverse engineer community engagement pilot project that I worked on with the Wilmington case study and with UCLA, I actually developed something new, never done. And what we did is a 1-year process of community engagement meetings, but not being basically plan and have a whole expectations on reverse. We actually came and we experienced the community. We did a lot of research on where the community actually, how they speak, what levels of knowledge they had, levels of understanding of the issues that were affecting the community. And we then understood that we cannot have any expectations from a community and having meetings online or using apps to, like Zoom, for example. And so we came up with a different approach. And can we go to the next, please? We evaluated and adapted to the cultural lingo of the community. 90% of the community are Latinx, 70% speak Spanish, so therefore we have the presentations in Spanish. And how do we establish the most effective and sensitive form of communication? It was a key here in this community to basically do a different type of approach and delivery of the creating presentations, since they were the ones that were doing most of the questions, and we were coming back with the answers that they wanted. And we try to avoid academic jargon and government language as well. We transfer that language. Next, please. The interpretation and translation, again, we prepare everything in Spanish, and we had interpreters in English for the people that did not speak or understood Spanish. And this made them feel more comfortable. And also we use very simple translation of the message that we were given and that they were asking for. Next, please. It's highly important, and this is the best practices. The community doesn't understand technical language, and most of the language used in science and the hard science, the community does not understand this type of language. Majority of the population in the world do not understand. It's a very small percentage. Therefore, we actually plan with the community. We let them lead. We avoid organizing and planning a series of meetings ahead of time. They actually shape the meetings. We never had any expectations, and we never imposed any information. And this, what did is that we created a trust and a partnership that the community now it's open to work with us and lead and develop, plan, and implement every project that they really want in the community to take place. Next, please. We use a simple method also to show some results through survey. We use the essential aspect of community engagement is to help measure knowledge and subject levels of understanding and degrees of language. And this helped us to show in matrix what they understood before and what they understood after. And also it helped us to transfer the information back and forward through government language, through academia language, and bring it to the people. And we work in a very consistent way. Next, please. And I want to, because of the time, I wish I could speak more, but thank you for your time. And if you need to connect with me, I will be more than happy. My wish is that you can use this reverse engineer community engagement process in every project that you do with your agencies, organizations, or departments. Thank you.
Thank you, Magalia. I don't know if you were able to hear our plenary speaker this morning, speaking from a Native American perspective, but the commonality of much of what Caleb had to say about um, interacting with his community and what you've just said, tremendous commonality, really. So thank you for helping to bring that home. So I think Magali's perspective has helped us to understand just how important it is and the desire for more relevant air quality monitoring, which allows me to segue on now, if I can successfully navigate to our next speaker. And I'm very excited to have Adrian Dubois here with us. And let me pull up my intro. Adrian is the founder of purpleair.com. A lot of people have heard of Purple Air at this point. He invented the original Purple Air sensor. He built it himself and proceeded to build a company which is now deployed over 30,000. I think it's over 35,000, but you can correct me, Adrian. Sensors all over the world. And you can go to their purpleair.com website and see the global map of essentially real-time PM 2.5 readings, which is pretty amazing. But with that, let me turn it over to you, Adrian. And yeah, just please tell me when you want me to advance.
All right, thank you. And thank you everyone for having me. It's a pleasure to give you a talk about Purple Air. Can all hear me okay?
Yes.
Okay, so we can go to the next slide.
There we go.
As mentioned, I made the first Purple Air sensor, and I did that back in 2015. We have this big gravel pit behind the house, and I would watch dust blow out of that gravel pit every day. And there was no federal sensor for 20 miles, and I just wondered how much dust that was, whether it is above standards or what. And I asked myself the question, I said, literally, this is 2015, there must be a sensor that can measure dust in the air. And so I set about looking for one, and ended up designing and building the sensor that we had now. It's interesting that the start of Purple Air is kind of like environmental justice type of subject. It's being exposed to pollution from a large industrial facility near you. And it turns out that there is a lot of industrial, environmental justice related causes out there. And the thing that's common about all of the environmental justice causes is everyone feels very emotional about it. They're going through terrible times with it. It is traumatic. It is dangerous. It is something that no one wants to listen to. It seems the authorities don't really care. And so by measuring things, we thought in our situation that we might at least be able to shed a bit of light on it, let people see what's going on at night when it's dark, and just start some conversation. And I had no idea how big the conversation would become, because who is Purple Air? It's not us here in Draper who makes the sensors and me who does some programming. It's everyone out there. It's all of you who use the sensor, the data, in your causes, in your efforts, even if it's just curiosity or environmental justice, and researchers, everyone. It's been really incredible to see it grow and to be part of it, and to just see how we can affect everyone's lives out there and help to give hope to something that seems sometimes hopeless. We can go to the next slide.
Working on it.
So Purple Air's mission is to provide precise and highly accurate real-time air quality data for everyone. And when I say everyone, I mean, we don't want you to have to log in or sign up or subscribe to be able to go and view the map and see what's going on in your neighborhood immediately for free. And our mission is to actually share that data, share air quality data, get everyone to become more aware. We want to do that by manufacturing high quality, low cost air quality sensors. We do that ourselves. We're an employer here in Draper, Utah. We don't just have the sensors made in China. We make them ourselves, test them and support them and everything from here. And we want to provide the high quality services that are needed to store the data, serve it, visualize it. Without those, it's very difficult to share data from a sensor like this. You have to be able to share it with your friends and others, easily download it later and analyze it later. And our map is a big part of that. Next slide. So purple air sensors measure PM1, 2.5, and PM10. Unfortunately, PM10 is what comes out of the gravel pit, which was the original motivation for this. And planned tower devices, which are the laser counters that are inside the purple air, aren't good with PM10. In fact, very poor quality of data for PM10, unfortunately. So for the original purpose, they're not very good at monitoring the gravel pit, but hopefully in the future we will solve that. However, PM2.5, they are extremely good, and PM1 also extremely good at measuring those, to the tune of about 97% R-squared or correlation score with federal reference methods. That means that if you go and find evaluations done by South Coast, AQMD, and others, you'll find that it's a very, very high correlation, that the trends, the up and down of the trends, match very, very closely with expensive sensors. We also measure temperature, humidity, and pressure, and we can measure other things like the network latency and stuff like that. Purple can also be used to determine power outages based on the fact that a whole area has just gone dead. We measured the Tunguska volcanic explosion. The shock wave from that traveled around the world was seen on the purple air pressure readings. And so it can be used for a bunch of other things that are not necessarily directly obvious. Next one. The purple air map is our main output of data on the next slide. It's what everyone can use to view the data in real time. It updates itself every 2 minutes. You don't have to press refresh. You can just sit and watch it update as you watch. And it's used by everyone from schools in California to determine when to shut down for wildfire events, to people that want to go running or cycling and want to choose a best time to do that and avoid the pollution. People with asthmatic children have told us that we help them to manage their child's asthma better by knowing when to let the kids go outside and play or not. And they can improve the symptoms by just managing that based on the data that comes from the map. Next slide. Our API management tools let you create API keys that if you want to access the data programmatically, you can do that as well. And you can incorporate it into other applications or reports or studies that you might want to do, so you can access the data through a programmatical way. Next slide. So use cases for purple air. It's a good survey tool. It can fill the gaps. We can re-engage with the community. It's an educational tool. It helps with disaster recovery management. And we'll go through each of those in more detail next. So the next slide is the survey tool. You can use low-cost sensors, purple air sensors, to determine where to place federal reference sensors that are more expensive and difficult to deploy in volume. And so you might use purple air sensors to decide where to place the federal reference one. So a good example is the Arkansas stump dump fire, where there was no EPA sensor and there was a stump dump that had literally a landfill that had a bunch of tree stumps in it, and it caught fire, and there was smoke coming out of the ground. And the locals were complaining about it, and no one was listening to them. They put some purple air sensors around there, and then the EPA noticed because they got on the news, and then the EPA put their temporary sensors there as well. So you can kind of survey or draw attention to something that needs to be looked at. Filling the gaps is the next slide. And purple air data is really good at filling in the gaps in between regulatory sensors. So if you have a regulatory network and they spread out as they are, and you have purple air sensors in between, you can then use the regulatory network to calibrate, as it were, the purple air sensors, and then find the in-between data and fill in your map. This example is a South Coast AQMD grid map product, which is a great improvement over what they had before this, which was a county level map from their county level sensors. Then number 3 is re-engaging with the community. This is kind of an important one, or a big one, because I remember in the very beginning, South Coast said to me that one of the things that they liked about Purple Air was that it helped them to re-engage with the community about air quality. Because since the 60s and the 70s, where air quality was visibly very terrible, air quality got better and better with all the regulations that were put in place on vehicle emissions and such. And by the 90s or 2000s, the attention on it was much less. There was like, oh, we don't really have a problem anymore. Why do we have to do all of these things? And people started forgetting about the issues of the 60s and the 70s. And so this gave the regulator the ability to reopen that conversation, get the community involved in collecting data, seeing that there's still problems, there's still hotspots, and there's things that we need to do. And then the wildfires started and everything changed. So number 4 is as an educational tool. On the next slide, Purple Air is a great educational tool. In the very beginning, Purple Air sensors were being used in a school where the kids' task was to look outside, and this was young kids, like 5, 6-year-olds, 6, 7-year-olds. They were asked to look at the air outside when they came to school, and then when they got to school, they looked at the reading on the sensor, and they wrote on the wall what their observation was and what the number was on the sensor. And so they started associating the number on the sensor and what they're going to see outside and linking those together. That's a very simple example of a great project for very young kids to raise awareness, all the way through to PhD students who use terabytes of data for a PhD project on studying the effects of air quality on a large scale in some way. And then number 5 is disaster recovery management. We can help with shutting down schools in wildfire events. We can help understanding where VOG from the Kilauea volcano is. We can help in all sorts of things on a high resolution around where the smoke is, where it's moving. People use Purple Air, for instance, to decide where to go for the day in California to escape the smoke when they're all socked in. Then the next slide is our challenges. So, you know, the challenges that Purple Air face is, number 1 is the data. It's a huge amount of data. Storing it, making it available, being able to process it, it's no small task, and it's one of our big challenges. And the other one is education. You have to educate our users every day. We do a lot of education. And that's just answering simple questions or doing talks like this and trying to share some of what we've learned. And the biggest thing is the difference between regulatory and low-cost sensors. Like, people will say, well, why is the EPA sensor reading this and the Purple Air is reading that? And they might have the Purple Air on real-time readings every 2 minutes, and the EPA is hourly readings or 24 hourly readings, and they're trying to compare it. So we have to educate them on, okay, firstly, make sure you're looking at the same averaging period. And then you have to apply the correction factor to the data. So you've got to make sure you've chosen that on the map. And then it's like, well, what's that and why is that? And that's a whole different subject. So it's out of scope of this. But if anyone was interested, we do have good articles on our community at community.purpleair.com about the differences between Purple Air and light scattering readings and gravimetric readings like the EPA does. And, you know, a bit of research on the differences and why they read different will answer a lot of questions. But you can also email us if you have any questions like that too. But education is a big deal. And it was said earlier that most of the population doesn't understand when you start talking about mass density and conversion factors and R-squareds, and you've lost them already. So you need to be able to explain it simply. And really the simple answer is the difference between a ping pong ball and a golf ball. You know, the ping pong ball is really light, the golf ball is heavy, and they're the same size roughly. And this is different particles. One particle is light, one particle is heavy. You're seeing that particle and you're assuming it weighs something, but it doesn't really weigh that. And that explains a lot of the differences. Wildfire smoke is lighter in particles for a size than dust from a gravel roadway. And that's one of the reasons, the big reasons for the sensors reading differently. Another one is the reason for the networks. EPA networks are there to measure over weeks, months, and years the effects of regulatory changes, vehicle emission standards, and they don't want to be measuring the output from that local restaurant that's coming across your yard every day. They want to be measuring regional levels so that they know that their big missions are being accomplished, whereas you want to know that you're safe in your yard. And so that's what Purple Air is about. And the EPA network has a different purpose. Next slide. Our plans for the future is to continue building our network and making better sensors and maybe measuring things like gases and SO2 and NO2 and ozone and VOCs and other things that people are interested in, and improving our products overall. And with that, it's the end of my presentation. And thank you so much for having me. And it was a pleasure talking.
Thank you very much, Adrian. And I'm brandishing one of your sensors. This is my home backyard sensor that I briefly brought over here to Asheville, and hopefully we'll be able to re-implement when I come back home seamlessly. I hope. But this is what one of them looks like in the flesh, and I will be demoing during the research showcase. So if you want to actually come up and touch one and see the laser counters and stuff like that, look for me at a table during the research showcase so we can talk about it.
Very good. Thank you.
Well, yeah, yes and no. That's a subject I don't want to get into now in the interest of time. But so again, thanks, Adrian. And I think that gave us some ideas of, as you said, filling in the gaps. Next, it is my pleasure to introduce Colleen Rosales, and she is the Strategic Partnerships Director of OpenAQ. She's an atmospheric chemist by training, and she holds a PhD in environmental science from Indiana University. So come on up, Colleen, and let's see if we can bring up your presentation without too much difficulty. And I will get out of the way and let you drive. I think we should be good. I'm using this down key to advance. Okay, take it away. Thanks.
Thanks so much, Steve. So I'm honored to follow Adrian and all the work that Purple Air has done. So I'm gonna take you a bit into the data side of things. And I want to introduce you OpenAQ. If you haven't heard of OpenAQ before, I'll do a little bit of a walkthrough. And I'm happy to do also a more thorough walkthrough in the research poster showcase later on. So I have both a poster and I'm available to do the demos as well. So OpenAQ, we're a very small nonprofit. We're a small but mighty team of 3 wrangling the world's air quality data. We started out as sort of a research initiative, research project focusing on aggregating reference monitor data. And our founder, Krista, who's also an atmospheric chemist, together with her husband, Joe Flasher, were the first ones to, aggregate all of these reference monitor data worldwide. And with the increase in the, air sensor data, we've started also ingesting air sensor data. So we became a nonprofit organization as of 2018. And you can read more about that story in the short link below. But today what I want to talk about is the platform. So we're the world's largest open source air quality data aggregator and harmonizer, very much focusing on the aggregation side. So we don't collect the data ourselves. We don't generate these data ourselves. We're an aggregator and we display this data on a public platform. So we focus on criteria pollutants as listed down below. And then also we put this out in many different data products as listed in here. So there's the API, the archive, which is accessible via AWS S3, and then the Explorer, which is the one that I will demo in a little bit. We also have different data products like the command line interface and the Python wrapper. And we offer trainings to use many of these products as well. So say, for example, you're interested in giving, say, a class or a lecture in your class about OpenAQ, I'm happy to assist in that as well. So like I mentioned, we aggregate both reference monitors and air sensors. As a nonprofit, OpenAQ serves primarily in the past, it's a lot of, scientific usage. Up to now, maybe up to 50% of the usage of OpenAQ is still a lot on the scientific side. So, but we aim to also develop many tools so that the non-scientific use is also increasing. So these are two of the fun use cases that we've seen. This is more, we don't own or control any of these. They use the API for these purposes. And so one is Smoky Air Pollution Bot. It's a chat bot that one can chat with in Messenger or WhatsApp, ask what's the air quality outside, and it will show these cute cute things, and then also tell you what you should do to avoid like hazardous levels of air pollution outside. There's also Shoot I Smoke, which converts effectively the pollution levels outside into the number of cigarettes smoked, equivalently. And then other use cases as well are, so the Bloomberg Green PM 2.5 tracker puts the air pollution data and overlays it with population data. Sorry, the image there is quite small, but you'll see like sort of hotspots of air pollution based on this real-time data. So that's more of an evidence-based journalism. So on the right side is Clean Air Catalyst. This is a USAID funded project that is led by WRI and EDF, so alphabet soup, but World Resources Institute and Environmental Defense Fund. It's a 5-year long project now in, I think, year 4. Our part here is in the data management and engineering, but mostly this whole project starts from, the deployment of the reference monitors in these 3 areas up to policy making and whatnot. And so we play this, kind of small role in data management and engineering for these cities. And then maybe this is more of interest to the audience today. So machine learning and air quality data, with the amount of data that is out there for air quality, it's inevitable that we should be using this for predicting and forecasting. So these two are more focused on those. So AQAI is a UNICEF venture fund-backed organization. And they're using machine learning for predictive models in areas where there's little to no air quality data, such as in Latin America. And then predicting what we breathe, and the follow-up to that which is Peace for EEJ, which Magali actually was part of the cohort where we did the Peace for EEJ workshops. This is a forecasting algorithm for air pollution events developed based on time series measurements of satellite and ground data. So it's combining the data that's in OpenAQ and then satellite data from NASA and then some machine learning to have the 10-day forecasting models for the city of LA. And then, so that's the website on there. And then the Peace for EEJ, which is the next part of that, incorporates more socioeconomic data. And we are having the help of the team of Magali and the rest of the folks in Wilmington and other areas that we identified in the LA area to have the models be better informed. Because as Magali had shown a while ago, the areas might be showing green, but in reality, the lived experiences are not, shown in the models. So, yeah. And then, so what I want to do a little bit of a walkthrough today is our sort of data visualization and more on the, interactive features of OpenAQ. So like I mentioned a moment ago, we're more in the data engineering, data management side in terms of aggregating, harmonizing, standardizing all of these data. But for the data to be usable by, other than scientists, we have to also develop a lot of these tools. And so what I'm going to show a little bit later will be the Explorer, which is more of into the data analysis and data visualization part. So what I'm going to show is what we call the custom lists or lists. And then if you wanted to do the walkthrough on your own too, or revisit it at another time, the short link is up here. But the reason why we develop lists is that we see a lot of use cases that's more of the comparative type, or folks see the benefit of having being able to see many locations all at once and being able to compare all of these locations all at once. Kind of like how you have bookmarks in your browser. You favorite or you star your websites that you visit often, or you want to see often. So that's sort of the idea behind lists. And so yes, just some of possible uses that a list can have. And so you can see the platform at explore.openaq.org, or even if you go to openaq.org and click explore the data, you'll be able to see it there. And then this one, so I'm just showing here the sidebar and kind of a zoomed in view of the map. And then you'll be able to add, the location to a list. On the sidebar here, you see some data and then what is being measured by that monitor. And then also when was the last measurement and whatnot, just some spark plots and whatnot. And then this is, showing multiple lists on the sidebar. You're able to create lists and whatnot. And then also you're able to see comparatively all of the locations that you've marked in your list. And then it's also visible in a map version. So say, for example, you're planning to put your sensor or to put your reference monitor in a location, and you're able to kind of map out where could be a possible place that I'll put my sensor or reference monitor. So that's the map view that is, side by side by the list view. What I probably don't have time to talk a lot about today, but might be useful to the audience today is the API. So this is actually our main data product and the main way that you can access the data in OpenAQ. The Explorer has a limit to the number of downloads. The API does too, but you'll be able to kind of more likely that you will be able to download more pages in a sense. And so if you're interested about that, I invite you to visit the documentation. We have a complete set of documentation. And then also if you're interested in the Python wrapper or the command line interface, they're in pre-release. So go easy on them. But yeah, we welcome your feedback on all of these things. And then I'm also happy to talk more about these in the demo later. And then actually that's it. And I hope to see you later in the demo and poster session and talk more about OpenAQ. And so if you either are in the provider or the user side of air quality data, I'd be happy to chat with you. Thank you.
Wow. Colleen, we were a super achiever on time. I was more like 10 minutes. Thank you very much. So next, bear with me while I work on logistics briefly. I'm very excited that we have Andrea Clements with us from EPA, my old agency. And let me bring up her presentation first, and then I'll introduce her. Here we go. Slideshow. I almost am starting to feel like I know what I'm doing here. So Andrea, she's a research physical scientist with US EPA's Office of Research and Development based in Research Triangle Park, North Carolina. I'm going to shorten this a little bit, but she's leading efforts to evaluate sensor performance. So looking at a whole bunch of different sensors, right? Test the usability of sensors for a variety of applications and a bunch of related stuff. She does hold a PhD from civil and environmental engineering from Rice University, as well as a number of other degrees. And Andrea, I'm going to let you, and I should explain, well, you can see it on the screen, hopefully. She's going to be talking about Redigo. I had to learn that it was pronounced Redigo, and my mnemonic was, okay, like retina, because I thought it would be Retigo when I first saw the acronym.
Actually, people say it both ways.
I heard you say Redigo.
Yeah.
Andrea,
Up and down.
please take it away, and I've been putting this down key to works well. Advanced.
That sounds great.
Okay.
Great. Well, it's lovely to meet everyone today. Thank you so much for having me to talk about Redigo. But I'll also just throw in there a few lessons learned about sensors along the way. So my work doesn't like that. We'll use this. We're good. Okay. So today, like I said, I was asked to talk about Redigo, which you can call Retigo. People do that too. It's not a big deal. But I'll talk to you a little bit about the problem that we were trying to solve by creating Redigo, how we went about doing that. I'll give you kind of a very quick overview of what it can do, and then connect you to some resources if you want to learn more about this tool or about our research with air sensors. So as you've learned today, air sensors have great promise, and they're becoming more and more popular, especially for communities who are really interested in trying to collect their own air quality data where they live and work. They may have a variety of goals in trying to collect that data, whether it's trying to prove to someone that there is a problem that needs to be addressed, or potentially being able to advocate for themselves for a change that they would like to see happen in their community, all the way to just influencing personal decisions. Like Adrian said, where am I going to exercise today? What time of day am I going to do that? Where's the best place to protect my family from wildfire smoke? So we think that all of these goals are really important. And what we're trying to do is give people the information that they need to effectively use air sensors and to tell their stories. So to tell a story, you often need data visualization. And if we can combine the air sensor data that we collect with other types of data sources, we may be better able to understand the data that we collect and influence others to take the actions that we want. Now, each group has a variety of needs. And so what we've tried to do is create a tool that can be adaptable and to help people create the visualizations that they need. So just very quickly, our research really shows that there are a number of air sensors on the market today. And just because the sensor is on the market and it claims to be able to measure pollutant, doesn't mean that it can't. I think that's a really important lesson that we want to make sure that everyone walks away with. Some sensors are still random number generators. Others, and I'm not joking about that. Other sensors are very good at helping to understand the trends in air pollution. So when concentrations go up, the sensors readings go up. And so we can trust that information to help us make some decisions. Some sensors are influenced by other things happening in our environment. So for instance, they might be influenced by relative humidity. And so sometimes they give a false positive reading when it's just humidity or water in the air. We have other sensors that need sort of some data cleaning and some data correction in order for us to trust the number that's coming from that sensor. And still we have others that are performing pretty well, and we actually can trust that number. And it's often because the manufacturer really understands how the sensor is making the measurement and has done some work on the back end to account for all of those other interferences in order to give us a number that we can trust. So tools like Redigo are actually really great because they can help us put that sensor data into context and to show others if we should trust that number or not. Now, one of the great things about air sensors is they often produce data very quickly. We call that real-time data. which means that, on the order of every second or every 2 minutes, we might be getting a reading of our air quality, which is really exciting because we can make some of those decisions that we've talked about, but it can also be intimidating if we don't have the right tools. And many of the people, communities especially, who want to use these tools don't necessarily have the data analysis tools that we might need. So for instance, maybe they don't even have the internet, like was mentioned before. Maybe they don't know how to code. And so what we're trying to do is to lower the barrier for entry. We also realize that a lot of sensors on the market today create data with various formats. So there's a need to organize the data, to harmonize it, and then to visualize it. And Redigo not only uses sensor data, but we're also talking about bringing in satellite data and other types of data to compare. So there's more harmonization that has to happen there. And currently, there's not a lot of tools that meet all of these user needs. And I won't even say that Redigo meets every user's need. However, we are trying to target people who maybe don't want to spend the time or don't know how to code, people who want to be able to compare their data to other data sources, and who want a customizable visualization. And so that's what we were working on doing. So just a very brief overview. Redigo stands for the Real-Time Geospatial Data Viewer. When I say real-time, I'm really meaning high time resolution data. This is data that people have collected normally in the past. It could be, I've just finished a driving route and now I want to put my data into this tool in order to visualize it. It is free, it is web-based, and it can quickly allow you to visualize your data. In fact, we have some air resource specialists out on fires right now who are collecting data, mobile driving routes. And as soon as they come back to base camp, they can visualize this and understand where the smoke is right now. Very helpful. I mentioned you don't need to know how to code. We do want you to upload your own data set. So that sensor data that you have collected. And if you choose, that data goes nowhere. It stays on your computer and it's visualized from there. If you want, and this is something that we really encourage people to do, we want people to share their data and make it open. So we've also provided an optional data repository for people to do that. And then lastly, we're able to compare the data that we've collected with several other publicly available data sources. Now, in order to use the tool, the first thing most people have to do is format their data file correctly. And I say correctly, that's very subjective, but correctly for this tool. So we need the data to be in something like a space or comma delimited file. We need to have the timestamp in a known standard format. We have to know the location of that measurement, what sensor made the measurement, and what pollutant was measured with its units. And so on the bottom is just an example of how people need to label those headers in order for it to come into Redigo seamlessly. If you have a sensor that measures ozone, but also PM 2.5 and also temperature and relative humidity, that's okay. They just become extra columns on this data file. And then I can visualize whichever aspect I want. And when the data is imported, the first thing that comes up is a screen like this, where we see a map on the top and a time series on the bottom. Now, initially, the tool is going to visualize the very first pollutant variable that was in your file. There are controls on the right-hand side that allow the user to say, oops, I actually want to visualize this other parameter that I collected. It allows you to choose things like the colors that are displayed on this map. It allows you to choose the minimum and maximum concentration that'll be displayed. And you can zoom this map in and out. At the same time that this data is being displayed, in the back end, we're going out, we're saying what other data might be available within this bounding box and at this time of the year in order to pull in other data sources that might be available to visualize. So I mentioned at the top, we have this customizable map. We have a time series on the bottom, which shows the pollutant or the first pollutant and how that varies over time. And we can use our cursor to zoom in on specific times within this time series if we want, so we don't have to look at the whole frame. And the graph that we've created can also be exported so that you can put that into a PowerPoint presentation or a newsletter or something else that you might want to share with your community. This particular data set was collected on a mobile monitor. So this is a car that was driving around collecting this data. So at the very top, there's a play button and the little marker, which is a little red dot right here, the little red dot, will move along the map in time if you hit that play button. And then down at the bottom, there's a little black circle, and that circle will also trace your time series in time. So you can see where you were and what the concentration was at that time. But there are a lot of other options that you can do. So I mentioned that there's a toolbar on the right, and with that toolbar, you can actually choose some other plots and graphs in order to visualize. So this is an example of what we call the analysis plot. That's the second one on this list that's a check mark. So I just have to hit that toggle bar and I say, I want to visualize this map. So this map allows a user to determine what the concentrations were as a function from a point or a line. So in this example here, I might be interested in how this pollutant varies from distance from this roadway. And so what I've done is I've drawn a line on that roadway. It's in green. And now all of my data is calculated as concentration as a function from distance of that road. So I can better understand if this road is impacting my air quality. If my data also had wind speed and wind direction loaded, I can also create a wind plot. And so here I can investigate how my concentrations change as a function of wind direction or wind speed. And lastly, I can create a scatter plot that I can compare two variables. And this is extremely helpful for a number of different applications. So for instance, I mentioned before that some sensors can be influenced by relative humidity. Well, I can plot my pollutant and relative humidity and look to see, is there a relationship in my data? And this can quickly visualize that for me. The example that Steve showed of the purple air sensor, it actually has two sensors inside. I could compare sensor A to sensor B and make sure that that sensor is healthy and functioning. And that's one of the checks that we like to do when we're using purple air data. And lastly, and probably most importantly for most people, is I can use this plot to look at my sensor data and compare it to a regulatory monitor and see if those concentrations are similar or not. And that helps me understand, are they similar, are they not? And if they are dissimilar, do they still have a relationship? And if they do, maybe I can have a correction equation that makes them more similar to one another. There's also a way in which you can compare the data that you've collected with other data sources on the map. And here is just an example of 3 different data sources that are easy to pull up with just a click of a button. So the first one are these tiny little squares, and those are actually purple air sensors measuring PM 2.5. So through an agreement with Purple Air, we actually have a repository of this data. And so when someone says, I want to compare to Purple Air, all they have to do is supply their read key, and then we can serve Purple Air up onto this map. And now I can compare my data to any one of these sensors on the map. I can compare just by color here, or I can click on them, and then now I can create some of those plots we just talked about. Also on this map, you'll see some circles. There's just 2 of them. One up here in the top in green and one down here at the bottom in blue. And these circles are AirNow monitoring sites. These are the regulatory monitoring sites operated by EPA and our state and local partners. So here we're measuring PM 2.5, but I can also pick AirNow sites that measure other pollutants as well. And then lastly, there's a square here in the picture. And this square is a METAR weather reporting station. These are often found at airports, and they can give me information about the temperature, the pressure, the wind speed, wind direction, things like that. And so that's available for comparison as well. We've also been able to pull in a number of satellite data products, and I think this is especially important when we're looking at things like wildfire smoke. And so that's what's shown in the examples on the right. Here we have a mobile monitoring track that was collected by one of the air resource specialists attending to a fire in Colorado. And the data they collected was compared to a visual image from a satellite in that top right. And then on the bottom to aerosol optical depth on the bottom. And so on the top, we can see that there is a plume of Sonoma oak, but we may actually ask, is that smoke or is that a cloud? And so aerosol optical depth can help us understand the difference, and then we can start comparing our data. Now, there are still reasons why they may not jive, especially if we're collecting at surface level, but the plume is a lot. But this can help to tell our story and maybe help us interpret the data. So we want to make sure that this data is available. So some of the things that we have from satellite data products are fire detects. We have the true color imagery, we have aerosol optical depth, and we have some column integrated NO2 right now. We're adding to this list as time goes on. And lastly, we have a number of export features. I mentioned how we like to be able to save a visualization and put it into a newsletter or something else. And so we've made that available here. So many of the images can be saved to your personal computer. That scatter plot I talked about, you can actually export the scatter plot, the data that was used to collect it, all of the statistical comparisons in the upper right-hand corner. And I mentioned maybe you're comparing your sensor data to EPA monitor data. You can actually correct your data. So it'll give you the correction equation to make those two data sets more comparable. And lastly, we do know some people who like to use the Ready-Go visualization, but their data was collected in 3D. And so we've created a feature where you can export a data file that can easily be uploaded to Google Earth so that you can visualize your data in 3 dimensions. So version 4 of Ready-Go was released earlier this year. We hope that you'll give it a try, check it out. I mentioned a couple of things that we're continuing to add, including tempo data, a data file format checker, because some people have trouble with that. We're adding on some data quality assurance functions and some fire parameters that may help people interpret some of the data. If you have other ideas, we would love to hear it. We want to know how you're using this tool. So I encourage you to get in touch. And lastly, I just want to point you to the Air Sensor Toolbox, which is a website where we publicize all the information and research that we're doing related to air sensor technologies. I want to point you to the Enhanced Air Sensor Guidebook, which I think is a really comprehensive guide for getting started with air sensors and interpreting their data. And then lastly, a series of resources that'll help you use Ready-Go. So with that, turn it back over.
Well, thank you very much, Andrea. And when I saw Andrea speak at a webinar, the clarity with which she explained that the bottom line is to put the data and information to use to protect people, it was really striking. I thought that, it's like, yes, the data and the information are interesting, but they're also consequential because, we're trying to protect people, their health. And so to kind of connect the dots between the information and protecting health, I think is really important. So with that, and also it's a nice segue because you just mentioned tempo, and our next and final speaker is Danny Kaufman. And I'm going to try to shorten his intro slightly too, but he supports NASA's Atmospheric Science Data Center. And they are archiving and distributing, or will be distributing, data from the tempo instrument. So I'm going to skip the rest of it in the interest of time, Danny, but thank you very much for coming. And I've heard a lot of interest in tempo, so it's great that you've been able to come join us and talk about it. Oh, and I'm sorry, I forgot to bring up your presentation, so let me do that. Give me a second. And then slideshow. And we should be good to go. There seem to be various ways to advance. I thought I was having good luck with the little down arrow here. So okay, I'll do that. Take it away, Dan.
Okay. All right. Thanks, Steve. It's great to be able to share a little bit about tempo with you all. Yeah, I'm Danny Kaufman, at the Atmospheric Science Data Center, like Steve said. This presentation is just a kind of brief introduction to Tempo and its data. And it's material that's been put together by myself as well as Hazem, who's also from ASDC, the Atmospheric Science Data Center, and then folks from the science team of Tempo, Carolyn and Gonzalo at the Harvard Center for Astrophysics and Smithsonian. And there's a lot of other folks that go into making this data available, both ASDC and a bunch of other organizations as well. So just the brief primer on it. So Tempo is a satellite that was launched last year, and it's providing hourly measurements, hourly scans across North America during daylight hours. It was NASA's first Earth Venture class instrument, which is kind of programmed for competitively funded and more relatively lower cost missions. It was selected in 2012. It's in geostationary orbit, and this means that it's farther away from the Earth than a lot of other, again, relatively low Earth orbit satellites, where low Earth orbits are ones where they're orbiting maybe more than a dozen times a day, and they're typically making global measurements. And as opposed to that, Tempo is much further away, and it orbits the Earth at the same period as the Earth's rotation, which means that it stays in the relatively same place above the Earth's surface. So that means that it can provide continuous coverage of North America. Although it's not providing global coverage, it's providing more higher temporal and spatial resolution data. The baseline data products provided by Tempo are ozone, both total column ozone measurements and ozone profiles, and then nitrogen dioxide and formaldehyde. Tempo is not up there alone. In addition to two other geostationary atmospheric composition satellites that are meant to complement one another. You'll see on the right-hand side, GEMS. This was another geostationary satellite launched in 2020 that measures over much of Asia. It's launched by the South Korea. And then Sentinel-4 in the center there is to be launched by the European Space Agency to cover much of Europe and North Africa. And that's scheduled to launch in 2025, not yet launched. And then you can see kind of the general spatial coverage of Tempo going a bit south of Mexico City and then up into northern Canada. Tempo has a couple of different kinds of scanning operations that it performs. So in normal operational mode, it scans from east to west, and the mirror in the instrument actually steps along from east to west, and over 1,000 steps of that mirror from east to west. And as it does it, the whole time there will always be 2,048 pixels in the north-south direction. And the spatial resolution on the ground is approximately 2 by 5 kilometers squared, and that's at the center of the field of regard, which means it's like viewing area. And because of the curvature of the Earth, that resolution is not the same. In northern Canada, it's about twice that resolution. Tempo also does what we call optimized scans. So during the morning and the evening, when parts of the North American continent are still dark, because like in the morning, the western part of the continent is dark, and in the evening, the eastern part's dark, it will just scan at a slightly higher temporal resolution those parts that are actually lit. So in the morning and then evening, you might get like something like 40-minute scanning periods. It also provides twilight scans during just before morning. It will still measure radiances. It won't make trace gas measurements of ozone and nitrogen dioxide and formaldehyde, but it will provide radiances that you can see like city lights. And then there's also this is sort of rare, but it can provide much higher temporal resolution scanning frequencies for special operations. And these are ones where there's a particularly interesting scientific research question that has a lot of value, that it gets put, the proposed scanning plan gets put to the Tempo science team, and they have to approve it. And that's because there's a trade-off. If Tempo is doing these high resolution scans, then that interrupts the normal operations of the hourly scans across the continent. Okay, so this is an example of the spatial resolution of Tempo in comparison to some of the other related previous satellites, ongoing satellites. So the other low Earth orbiting satellites, and you can see this like over Washington, DC, which is shown in the center. And you can see how the Tempo measurements are about half the pixel size of a tropomi pixel. Although tropomi does global measurements, Tempo is this higher temporal resolution as well, in addition to the spatial coverage. Now onto the specific data products. This chart, I'm not going to go each cell, but basically you can see the three baseline products, trace gas measurements at the top. We have NO2, formaldehyde, and ozone, and then cloud. Now, Tempo provides data in different levels of processing, like other NASA satellites, where level one data, which are not shown here, are the radiance measurements that are geolocated, but they're not these like derived geophysical estimates. And these products have been available for the past 2 months. Since May. They're also level 1 products as well. And the level 2 products are provided at the native spatial resolution of the Tempo satellite, so that like that 2 by 5 kilometer spatial resolution. The level 3 data processing level of data are the same products, but then regridded onto a more regular grid, so you don't have those like differences in spatial resolution across the continent. And these are the level 2 data are, because they're not regridded, they're provided as in the original file structure that's used for efficient network transfer, which is in 6-minute what are called granules, and these are the files. So for each scan, you would get something like 9 or 10 different files of those level 2 products, whereas level 3 it would be 1 file per scan. And the clouds at the bottom, which is also provided, and that's actually used as part of what's needed for producing some of the other retrievals. The last thing on this slide that I want to draw your attention to is that currently these are all provided at the beta level of maturity, and this is related to how much calibration has been done on the data. The products are considered minimally validated. They still might contain significant errors, and because of that, the science team is still recommending not making conclusive public statements about like the actual scientific results from the data. But they are available, and lots of interesting questions to look into with it already. Don't want to not give you a sense of what it looks like. So this is actually I'm going to start here, which is the quality, all of the information about the quality of the measurements. So before looking at the data variables themselves, it's very important to make sure that that you're considering the quality of the data. And there's a number of things listed at the top of this slide that indicate the various aspects of the quality. So there is a main data quality flag. There is the cloud fraction that is important to how much information is there, an estimate of the uncertainty, and so on. So these two animations are showing cloud fraction on the left, vertical column uncertainty, and then if I go to the next slide, you can see like what one would want to do with those data quality flags, which is apply those and then look at the resulting the remains of what's good quality data in there. So there are user guides that are that accompany the data that go into much more detail about the quality. But that's just something important to keep in mind. And in addition to that example of formaldehyde, here's nitrogen dioxide. And this animation is cool also because this is from level 2 data. So those vertical stripes that you see are actually showing the delineation of those granules, the 6-minute granules. So you can see in this animation, you can also see the optimized scans where it's not actually crossing the whole continent. And you can see those granules. And also you can see kind of some of the estimates of NO2 and all those high values over urban areas and how it changes throughout the day. So just a little bit of the behind the scenes of what's happening with Dempo. This is the kind of stuff that I actually spend most of my time with is this whole mess of all of the things that happen behind the scenes. So the tempo data are actually, tempo is an instrument that's aboard a communication satellite, and those data come from that communication satellite. They go to a ground station. The science team at Smithsonian does the decoding of it, does the processing of level 1, 2, and 3, and then that gets pushed to the Atmospheric Science Data Center where I work. All of that goes into the Earth Data Cloud, which is NASA's Amazon Web Services archive for cloud data that they're moving data to. And then users can then, anyone can then download it from there or access it in the cloud. As well, there's something called the Earth Data Forum that NASA provides where anyone can ask questions about the data or how to access it or anything like that. So 3 things I just wanted to highlight as far as like, if you want to try to look at the data: Earth Data Search, Worldview, and Earth Access. Earth Data Search is often kind of the first place people go to find the data. This is an interface that provides access to all of NASA's Earth observation data. And it also provides options for some pre-processing and transformation of the data. This is what it looks like if you put in tempo and search, and you'll see all of the data files that are available for tempo and can download it directly from there. Worldview is this imagery browser. So you can actually scroll, you can see on the bottom of this slide, like this timeline that you can scroll through and see the data at different times. This particular image is not tempo, but you can do the same thing with tempo. And actually, I want to mention here also that tempo are currently like any satellite data. It does take a while for all of those data to be processed, so it's not exactly real time because it takes quite a while for the data to go through that whole process of going to the ground station, getting processed, going to Earth Data Search, and so on. So you won't, if you go to Worldview, if you don't see data for that hour, it's because there's a lag time. Finally, programmatic access. I really love using Earth Access, which is this tool developed by NASA to streamline the process of actually getting NASA data programmatically. For Python, previously there were probably dozens of lines of code that would be needed to do authentication and actually then search and open data files, but Earth Access is a great way to do that much more simply. And reiterating Earth Data Forum, this is what it looks like, a place to ask any questions about tempo. And it goes right to subject matter experts that can answer whatever question you have. So that's all I have. You can see kind of the summary points right there. There's a QR code where there's a ArcGIS story map that has more information. Yeah, I hope that was a good introduction to tempo, and I'm excited to see it in some of these other tools as well, getting incorporated into EPA stuff and everywhere else. Yeah, thanks. Thank you very much, Danny.
Danny was our final speaker, and I'm looking at our time, and it's 5:26, so we theoretically have 4 more minutes before we are supposed to wrap. We went a little bit over, but all of the speakers were very conscientious about time management, and thank you for that. And a few technical issues, mostly on my part, slowed us down. But let me ask, does anyone have a burning question that you'd like to put to one of our people? That you think might be answerable in like 2 minutes. Ben, now we have a mic, or would you mind stepping up to the podium maybe? And
This was so exciting. Steve, you did such a good job putting this together. I was sitting while Andrea was talking and while Colleen was talking and going, hey, can Magali get sensors in her neighborhood, upload those to their, have them, viewable in your thing, and how can we get this going so that, so this can happen, so that people can look, is your tool mobile? Can you use it on a mobile app? And could people, look at the data that they're collecting on their own sensors in their backyards on Redigo? Great. It was super exciting, like hearing all of you guys in one brain saying, wow, things need to come together so that Magali has access to data and her neighbors, right? And it was great hearing from everybody. Magali, I don't know if you're still there, but thanks for sharing that. That was so interesting.
I admit, I was hoping that Adrian, who is still with us, I believe, would take some notes on what Magali is dealing with in Wilmington, and maybe might consider a little bit of pro bono help to Magali, because I think we, Karen Moe, one of our colleagues, has implemented a hyperlocal Purple Air Network in Cheverly, Maryland, a DC suburb, and has been stewarding about a dozen Purple Air sensors. So they're getting some very local data, and they have a number of EJ type issues in Cheverly. And anyway, yeah, I think Magali's passion for the community and her approach for involving the community is great. I'm hoping she'll get some help from the broader community. Plus, I know someone who might go out there and visit, we'll see. Well, listen, because of the time, what I would encourage, or Adrian, I don't know if you have any parting words maybe that you'd like to make. Go ahead.
We do have programs that give away sensors from time to time, or we can give a 10% discount, even for a couple of sensors if you're looking for some help. But talk to us if you're looking for sensors. We might be able to put you into a program that we call the Collective. We give away sensors every month, and you would tell us about your project and what you need. But the community can also get involved. They should take part, get sensors, deploy them. They can then be recorded in the Purple Air database. You can then analyze it in Retigo. You can take the data and use it wherever you need. So yeah, Purple Air is a great way to collect the data.
And I'm going to give Andrea, do you want to?
Yeah, I just had one more comment, and that is, I don't know if you know, but there are some sensor loan programs in different communities across the country. And in fact, almost every EPA region has at least one sensor loan program. Who they loan to, what equipment they have kind of varies across the country. But I also happen to know that like South Coast has their own program. So some of the state and local agencies as well. So if you don't need sensors for a long period of time, and maybe there's something out there that you can borrow, that could also be an opportunity if you don't have funds.
And I learned from the air sensor toolkit that Andrea mentioned, there's a program called W Smart that's particularly oriented toward wildfire issues, I believe, where EPA loans sensors for wildfire response situations. So the resources page, maybe I could bring that up again one more time. Andrea showed some resources and this resources document, that's the lower QR code or the bit.ly. A bunch of things are hyperlinked on that document. So, again, you can visit that and pick up some more stuff. Well, thank you very much for coming to this session, and I hope everyone feels like you learned some things. And it's a really important topic. I think with climate change, like it or not, we're going to have increasing issues with air quality. We're learning a lot more about the health impacts of poor air quality. And I think it's an area where the ESIP community can really do a lot to help. So one more time, thank you. Thank you very much and have a good evening. And like I said, I will be sitting at a table demoing the purple air sensor. So feel free to drop by and you can touch it. You can't take it, but you can touch it. All right. Have a good one all. Bye-bye. Thanks again.